Hello everyone, this is another video on statistical mechanics. We will be solving more questions. Right? So we'll continue from the previous session where we are done solved five questions. So there will be question number six. Right now, if the mean square fluctuations in energy of the system in equilibrium at temperature T is proportional to T to the power alpha, then the energy of the system is proportional to if the mean square fluctuations in the mean square fluctuations in energy of the system in equilibrium at temperature T is proportional to T to the power alpha, then the energy of the system is proportional to the mean square fluctuation in energy of the system in equilibrium at temperature T is proportional to T to the power alpha. Mean square fluctuations. Okay. So what is mean square fluctuation? Mean square fluctuation in energy. Mean square fluctuation is how much? Mean square fluctuation is can I guess daily. Then the average energy, what energy of the system is proportional to. Mean square fluctuation of the system in equilibrium temperature T is proportional to T to the power alpha. Okay. So average energy is related as. So we know what Delhi is what? We know Delhi square is equal to kb T square divided by del T of. Okay. Right. So Delhi square is proportional to what? T to the power alpha. Okay. I can write as Delhi square is equal to some constant A into T to the power alpha. Yeah. So now we'll equate these two because these are equal. A T to the power alpha is equal to kb T square del by del T of e to the power del by del T of E. Okay. So if I write it again, so AT square is equal to AT square. Sorry, AT alpha. AT alpha. AT alpha is equal to del by del T of kbt square del by del T of E. Okay. So now what? I will take this T square to this side. It will be T alpha minus 2 equal to kb. If I write it a bit like arrangedly, del by del T of E is equal to A by kb T to the power alpha minus 2. Now I will take dt to that side. So dE is equal to A by kb to the power alpha minus 2 dt. Now what? Integration. Okay. If I integrate it, it will be E is equal to what? A by kb to the alpha minus 1 divided by alpha minus 1. Yeah. So E is proportional to what? K to the power alpha minus 1. Alright. So first how I did it, mean square fluctuation. Mean square fluctuation is given. Okay. No, like mean square fluctuation is this one. Okay. And this is proportional to what given? T to the power alpha. This we formula we know is what formula we know? square is equal to kbt square del by del t of E. This is the formula we know. So we can solve this question. Okay, next question. Question number 7. For a classical system, for a classical system, a classical system of non-interacting particle, system of non-interacting particles in presence of a spherically symmetric potential Vr is equal to gamma RQ. Okay. So what is the mean energy? What is the mean energy per particle? What is the mean energy per particle? For a classical system of non-interacting particles in presence of a spherical symmetric potential, Vr is equal to gamma RQ. Spherical symmetric potential Vr is equal to gamma RQ. What is the mean energy per particle? What is the mean energy per particle? Alright. So see, classical system non-interacting particles spherically symmetric potential. So we know Hamiltonian for this one is Hamiltonian. We can write the Hamiltonian as H is equal to P r square. Why P r square? Because this is spherically symmetric plus gamma r cube. Okay. We know what is P r square. Px square plus Py square plus Pz square divided by 2m plus gamma x square, x square plus y square plus z square root over to the power q, isn't it? So that will be 3 by 2. Yeah, 3 by 2. So we know equipartition of energy, law of equipartition of energy. We need to calculate mean energy for the particle. Okay, so we need to kind of calculate the mean energy of Hamiltonian, right? So how we calculate it? See, we know from using law of equipartition of energy. This came in JS 2018. Law of equipartition of energy. We know xn del h by del xn equal to kBT. Okay, this is what the equipartition energy law of equipartition energy says. Okay, also px del h by del px is equal to p x square by m is equal to kBT. Okay, yeah, right. So if I'm okay, if I write it like this also, like we wrote what px square by m is equal to kBT. You can write it px square by 2m is equal to half kBT. Half kBT. Is that alright? And similarly, py square by 2m will be equal to half kBT. Pz square by 2m will also be equal to half kBT. Is that alright? Yeah. Okay. Now we know. Now what? Now I can write xn x del h by del x average y del h by del x average plus z del h by del z. So this is zy. Del y average is equal to how much? It will be how much? This one was what? X del h by del x was kbt. Yeah. This is also equal to what? This is also equal to what? This is also equal to square plus y square plus z square 3 by 2, which is equal to kbt plus kbt plus kbt. Okay. That is 3 kbt. Yeah. So 3, if I write on both sides, 3 gamma x square plus y square plus z square. Hmm. Yeah, x square minus square 3 by 2 is equal to 3 kbt. Okay. Yeah. So gamma x square plus y square plus z square 3 by 2 is equal to kbt. Okay. So this is okay. What will be Hamiltonian? Then Hamiltonian is equal to expectation value of Hamiltonian will be how much? See, PR square by 2m plus your potential. This is your potential. This is a actually what? Potential, isn't it? Because potential is this one. Hmm. So H is equal to this is what exactly px square by 2m plus py square by 2m plus pz square by 2m plus v. Okay. So this should be equal to half kbt, half kbt, half kbt plus half kbt plus half kbt plus v kbt. So 3 by 2 kbt plus kbt, that will be equal to 5 by 2 kbt. Is that alright? 3 by 2 kbt plus kbt is equal to 5 by 2 kbt. Yeah. Okay. 3 by 2 kbt plus kbt is equal to 5 by 2 kbt. Yeah. So this is the answer for the expectation value of energy, or like the mean energy per particle. The mean energy per particle. All right. Yeah. Next question will be question number 8. Question number 8 will be monoatomic gas. Monoatomic gas consists of atoms comes with two internal energy levels ground state E not equal to 0 and an excited state E1 equal to specific heat of the gas is given by specific heat of the gases given by monoatomic gas consists of atoms with two internal energy levels. Ground state E not equal to 0 and excited state E1 is equal to E. Specific heat of the gas is given by specific heat of the gases. Okay. Let's try this question because this came in jest. 2014. Ground state E naught is equal to 0. First excited state E1 is equal to 1. Specific heat of the gas is given by average energy. How much from this? Summation I Gi Ei e to the power minus beta Ei divided by summation I Gi e to the power minus beta Ei. So what is it? E to the power minus beta E divided by 1 plus e to the power minus beta E, if you check. Okay. So what is asked? Specific heat of the gas. Specific heat. So this is your average energy. What is the total energy? This is average energy. Total energy would be monoatomic gas. So 3 by 2 kBT plus this one. So 3 by 2 kBT plus e to the power minus beta E divided by 1 plus e to the power minus beta E. Right. So 3 by 2 kBT. So if we have to calculate specific heat, so specific heat is Cv is equal to del E by del T. So del by del T of this one 3 by 2 kBT plus e to the power minus beta I by 1 plus e to the power minus beta I. Here beta is what? 1 by kBT 3 by 2 kB plus del by del T of e to the power e minus e by kBT by 1 plus e to the power minus e by kBT. So if I take the derivative 3 by 2 kb plus 1 plus e to the power minus e by kBt, then del by del t of this one, that is e into minus e by kb to minus kbt. Okay, minus e to the power minus e by kbt into derivative of this one, that will be minus e by kb to minus e by kbt whole divided by 1 plus e by minus e by kbt whole square. 3 by 2 kb. So this will be what? 1 plus e to the minus e by. So kind of a recalculation you have to do yourself. Okay, it's a bit tricky this one. So for the final expression, that will be 3 by 2 kb plus e square by kt square e to the power kbt divided by whole square. So we the final expression for this one. Okay. Next question. So next question will be okay. There are some questions that come from a bit of magnetic field and all in statistical mechanics. Let's do this one question. One, a 2D box in a uniform magnetic field, uniform magnetic field B contains n by 2 localized spin half particles with magnetic moment mu and with magnetic moment mu and n by 2 free spinless particles which do not interact with each other, which don't interact with each other. Okay. The average energy of the system, the average energy of the system at temperature T is the average energy of the system at temperature T. A 2D box in a uniform magnetic field B contains n by 2 localized spin-off particles with magnetic moment mu and n by 2 free spin-off particles which don't interact with each other. The average energy of the system at temperature T is how much? Again, read the question. This question came in just 2016. A 2D box in a uniform magnetic field B, okay, contains n by 2 localized spin of particles. Magnetic moment is mu, and n by 2 free spinless particles which don't interact with each other. Average energy system. Okay. So see, the average energy of n by 2 spinless particles, free spinless particles, is how much is it? It will be E1 is equal to n by 2 into see 2 by 2 kbt. Why 2? Because it's a two-dimensional box. Okay, is equal to n by 2 uh, n, n by 2 kbt. Mm, wait. No, this should be your E1 n by 2 particles into kbt into two dimension 2 kbt. That will be n kbt. Okay. Now n by 2 the energy for average energy for n by 2 localized spin half particles, localized spin half particles is E2 is equal to n by 2. Okay. These are undergoing under magnetic field and magnetic moment mu. So minus n by 2 mu b. Mu is a magnetic moment, b is a magnetic field. Tan h mu b by tan h mu b by kbt. Okay. Tan h mu b by kbt. So average energy of the system E is equal to E1 plus E2. That is nkbt minus n by 2 mu b tan h mu b by kbt. Okay, that's the right answer. Nkbt minus n by 2 mu b tan h mu b by kbt. Okay. Mm. Next question, question number 9, I think. Question number 10. So it's one of the last question. System of particles of in lattice sites is in equilibrium at temperature T and chemical potential mu. Chemical potential mu. So multiple occupancy occupancy of the sites is forbidden. Okay? Multiple occupancy of the sites is forbidden. The binding energy of a particle at each site at each site at each site is minus epsilon. So the probability of probability of a site being occupied probability of a site being occupied is probability of a site being occupied is okay. A system of particles of n lattice sites is in equilibrium at temperature T. Chemical potential mu. Multiple occupancy of the sites is forbidden. Binding energy of a particle at each site is minus epsilon. The probability of a site being occupied. Okay, so probability of occupation or probability of occupying a site. Occupying a site is how much? The site is P1 is equal to 1 by e to the power beta e minus mu. Okay, plus 1. Here, what is the energy? E is actually minus epsilon. So let's put it. So E is sorry, beta, minus epsilon minus mu plus 1. So if I take minus outside, e to the power minus beta epsilon plus mu plus 1. Okay. I'll write it again. P is equal to 1 by e to the minus beta epsilon plus mu plus 1. So can I write it like this? 1 by e to the power beta, because the power is minus. So I can write it like this, plus 1. So this goes up, e to the power beta. Sorry, yeah, that's true. Epsilon plus mu plus 1. No. I'm sorry. E to the power beta epsilon plus mu LCM 1 plus e to the power beta epsilon plus mu, and this will go up e to the power beta epsilon plus mu divided by 1 plus e to the power beta epsilon plus mu. Okay. Hmm. Probability of this is probability of occupation. Suppose occupation O. So what will be probability of not occupation? What is the question? Probability of site being okay. This is the question is actually not occupied. Probability of a site being not occupied. Okay, that's the question. Probability of site being not occupied is how much? So probability of site not occupied would be how much? 1 minus probability of site occupied, isn't it? So I will write it as P not occupied is equal to 1 minus P occupied. What is P occupied? 1 minus what is occupied? E to the power beta. P 1 minus how much? Beta epsilon plus mu divided by 1 plus e to the power beta epsilon plus mu. So 1 plus beta, so e to the power beta epsilon plus mu, e to the power beta epsilon plus mu, 1 plus e to the power beta epsilon plus, so 1 by 1 plus e to the power beta epsilon plus mu. That is the probability of not occupied. Okay. So for n sites it will be what? For n sites, n lattice sites, no? There are n lattice sites, it will be this to the power n. Simple. Okay. That will be the answer. This will be your answer. Alright. Yeah. So we did solve 4 questions, 5 questions. Okay. And yeah, just practice these questions and try to solve more this type of questions so that it will help you in exam. Okay. Thank you very much.